This is going to be problems 8 through 18 on the atomic nuclei and radioactive problem set 1. I'm also going to include number 5 here from, I believe it's problem set 3. Kind of scroll through here and just make sure that that is the case. Yes, problem set 3. Okay, so now let's get to business. Go here and start working through this. Okay. All right. I'm going to kind of have this up, this on this screen, and you can see what I'm going to be writing and everything over here. That way it makes things a little easier. All right. The question, number 8, a 4 millicurie source with a 2.69-day half-life is implanted into a patient. So the prescribed emitted radiation is 2.8 times 10 to the 13th disintegrations. Estimate the time, the length of time after which the source has been removed. Now, I did not get this, and I think there is a typo here, and I'm going to go through the logic of what it is that I believe to be going on here. All right, what I have done is I've taken the activity we have here at the beginning, which is 4 millicuries, and I multiplied that by 3.7 times 10 to the 7th here. And I will open up this particular formula to kind of show you what's going on. And you can kind of see that here. I'm going to write all of this out. But I have changed it to this because this is the only way we're going to be able to get at disintegrations. If you know the disintegrations per second, then we can figure out the number of days here. So I've taken this and changed it into this. Now, how did I go about doing that, writing it out? I know some have stated that they prefer that. So let's get to that. I know that I've got 4 millicuries. So I know that I have 3.7 times 10 to the 7th disintegrations per second, which is what a becquerel is, if you remember that. And I know that that is the same as 1 millicurie. Now you can look that up on any of the charts or any of the documents that we've seen up to this point. I'm going to take that out for just a second. And what I've discovered here is that if you go into the book, you can see 1 millicurie is equal to 3.7 times 10 to the 7th becquerels. So just bear that in mind, that conversion factor is there. So now continuing on, if you do the math here, you end up with the 148, and that is 1, 2, 3, 4, 5, 6, and 48 million disintegrations per second. So that's where that number comes from. Now, the prescription here is going to be for 2.8 times 10 to the 13th disintegrations. So it's going to be this. I have typed this in here in order to be able to compute some of these formulas going forward, but I will again write this out. So we're looking at activity here. Now, how does this relate to the number of disintegrations or number of atoms that we have here? Again, if we go back into the text, we can take a look and we can see exactly what they're referring to here. We know that the number of disintegrations here, or the change in the number of present, which is essentially going to be your disintegrations, divided by the change in time, in other words, how long it took to get to that point, is going to be equal to minus lambda times n. We also know here that the activity is going to be related to lambda times n. Okay, so what do we know out of all of this? Well, let's flip back over here and let's write a lot of this down here. And I'm going to again initiate the drawing. I'm going to put these formulas up here, right here, so we know that the change in the number that we have divided by how long it takes to get that is going to be, it's going to be proportional here, or actually equal to minus lambda times n. Okay. Now, we also know that the activity is going to be equal to lambda times n. So from this, what can we come up with? Now, we know that the number of disintegrations that they are asking for here, we know that that's it, because we want that many disintegrations to happen with this particular implant. So we know what this value is. And once we make this particular replacement here, we would know that, and we would know this as well because we just figured this out. So if we know this and we know this, then we should be able to determine the change in time. Now, all we have to do is rearrange this particular formula, and what do we come up with? We come up with the change in the number here minus the activity. So we should come up with 2.8 times 10 to the 13th, and that's the disintegrations. And minus the activity, we have minus 148 million, which is a lot to write out, but we know that is the disintegrations per second. If we divide disintegrations by disintegrations per second, we should end up with some value of time. If we don't, we've done something wrong. What I found out when I went through all of this, and again, I went through this using a different method that used the half-life, but pretty much came up with the same answer here. So if you'll bear with me, if I take this and divide it by that, I came up with the same answer. Now that's how many seconds. I know how many seconds there are in a day because I took 24 times 60 times 60, which should get you 86,400, and divided this by that. Let's see, and I came up with that. So if I take this number divided by this, I come up with 2.2 days. This differs from what I see listed here is the answer. So this is what I am going to go with. So our answer in this particular case will end up being 2.2 days. All right. So I do need to make a correction about that. So, all right, let's move on here. We're going to go on here to number 9. Number 9, a source has a half-life of 12 hours and an initial activity of 10 millicuries. After 4 days, what is the activity? Okay, well, let me kind of walk you through what I've got here. So we know that this right here is the initial activity, which I'm going to write here, and I'm also going to write this out so that you'll remember. So this is the initial activity. All right, now I know this is the initial activity. I also know over here what the half-life is. And I also know how much time it has undergone. So why are all of these important? We'll get to that here in just a second. What is all this other scribble that I have on here? I know I've got a 12-hour half-life. If I have a 12-hour half-life, I can figure out what lambda is. Now, how do I do that? What's the method here? If you will remember in the book, remember the half-life is equal to the natural log of 2 over lambda. So all I have to do is take this and solve for lambda. And when I do that, that's what I come up with. Now, if I have lambda, what is my mechanism here for finding out what the activity is a little bit later on? Remember that the activity at some time, some later time, is going to be equal to your initial activity times e to the minus lambda t. I know this, I know that, and I know this. So what I am doing is I am saying 10 millicurie times e raised to the minus, and I'm just going to truncate this a little bit, 0.058. Ooh, quite a little better. And then since this is in hours, I need to remember that I can't just put in a 4 here for the time, because if I do that, I'm not going to get the right answer. What I have to do is I know I have 4 days, but I have to multiply that by however many hours there are in each day. It's 4 times 24. So in other words, rewriting this, e to the 0.058 times 96, because this is hours raised to the minus 1, and I have 96 hours. So those end up canceling. When I go through and do the computations on that, basically all of this is being taken care of here. I come up with 0.039. So if I took, and you can do this on your calculator, there's minus this times 96 if you just want to evaluate the exponential part. This is what you should come up with on that, and then you multiply it by 10 millicuries, and then this is what your final answer should be, 0.039 millicuries. So here I do agree with the answers that are out there. All right, so there's that one. Let's proceed on to number 10. Okay, calculate the percentage of activity remaining in a source after 10 half-lives. Okay, this is going to be something that you need to kind of conceptualize. The percentage of activity, again, this is going to come back to this particular formula. You just have to figure out exactly how to use this. So the percentage of activity is going to be the same as that. In other words, how much you have left after what you started with, this is going to be equal to the percentage you have left. Okay. So what we are going to do is we're going to take this particular formula and we're going to rearrange it even further. So we're going to come up with A divided by A naught is e to the minus lambda t. Now, we have no idea what lambda is. All we're given is that the source is going to be there for 10 half-lives. In other words, we know what the T is. The question is, what do we do in lambda? Well, let's hang on a minute, because we know from the previous problems here that this is true, right? So we know here that do a little substitution. Now that that's lambda, we also know it's going to be multiplied by T, which in this case is going to be that. And guess what? Those two cancel. And so what you're left with is that. So E is equal to minus the natural log of 2 times 10. Now, when I went through here and put that in here, you can put it in the calculator. I come up with, if you were to put it in as a decimal, you would come up with 0.001. What that means is that you take it and change it into a percentage. Which basically means you take the decimal point, put it over here, and put a percentage sign at the end of it. Okay. So that's a conceptual problem there. Hopefully it didn't trip you up too badly. So now let's move on to number 11. So we've got a radionuclide decays 1% in 1 day, and then calculate the half-life. And then we've got another radionuclide that decays in 70% in 1 day, and then calculate the half-life. Okay. So on part A of 11 here, how are we working this? Well, let me kind of work out some of the math here so you can kind of see what's going on. I know how much the radionuclide is decaying, so the question becomes, how do we work the problem? Now, I know that is going on. Never mind this. It's a straight scribble. Okay. I can rearrange this particular formula into this. Okay. What happens if I take the natural log of both sides? Oh, wait, I've got this backwards. Hang on just a second. It's bad teacher, bad teacher. Let's try this again. Okay. Every once in a while, I'll get something right. Let's see. All right, so I take natural log of n over n naught is equal to the natural log of e to this mess. Now, might be asking, why in the world are we doing this? We're roping this together with the review that we did a few weeks ago. And when you have the natural log of something that has an exponent, guess what? You get to take this exponent down and it becomes a coefficient. And the natural log of e is just 1. So you're left with the natural log of n over n naught is equal to that. And if you're looking for time, you can say the natural log of n divided by n naught over minus lambda. Now, I said all of that to say this. Let's take a look here at part A. It decays 1% in 1 day. Since it decays 1% in 1 day, I know that this ratio after 1 day is going to be 0.99 expressed as a percent, 99%. Using this particular formula or algebra as I go through, I know that if I take the natural log of this, which is essentially going to end up being this, this is my result. I also know that this is going to be equal to lambda or minus lambda times 1 day, because I know this is what I see in 1 day. So I know here that, and this is going to be a little tricky. I don't write it out. Okay. So I know here that if I take the natural log of, and I'm just going to write it 0.99 is equal to minus lambda times 1 day. I can find lambda by moving this and that over to the other side. So lambda is equal to and this ends up being my result. Because that's exactly what I'm doing here. 10 minus 1, this ends up being lambda. So I know that lambda is 0.01005, and technically that is, getting rid of all of this so I can kind of write this out. That is days to the minus 1. Those are the units here for lambda. Now, once I've got that, I can use this formula to figure out this. So essentially, in this case, what do I have? I have time is equal to the natural log of 0.99 all divided by minus 0.01005. And that ends up giving me this answer, which does agree with what's computed here. Part B is pretty much going to run the same way. The only difference here is that with part B, I see a decay of 70%, which means the ratio of what I start with over what I, the ratio of what I end up with over what I start with is going to be 30%, because 70% of it's gone in 1 day. But the same process goes along and the same solution process goes along. So I take the natural log of this, that's what that ends up being, minus lambda times 1 day. Again, using that same process of solving for lambda, I come up with 1.20. And then using this formula, once I figured out lambda, I can solve and I come up with 0.575 or 0.58 days. Okay. Hopefully that's not that confusing. I think you can kind of get it once you sit down and conceptualize that. So let's go on to number 12. So I've got a sample here of 10 millicuries of a radioisotope, and it decays 1.2% in a single day. That sounds familiar, doesn't it? So what is the activity after 1 day? Well, what I am looking at here is the activity divided by the starting activity, which is 0.988. It decays 1.2%, so I end up with 98.8%. Expressed as a decimal, this is where this comes from. What we're going to do here is basically the same type of thing as what I had done previously on the previous problem. Except here, guess what? Rather than use the numbers that are there, I'm using the activity. So I end up with this. Take the natural log of both sides. So I can solve for either lambda or t, depending on whatever it is that I've got. So in this particular case up here, I am looking for lambda first, since I know that this is what's happened in one day. Since I know that that's what's happened in one day, then I know that lambda is going to end up equaling, sorry for the mess, the natural log of 0.988 divided by 1 day. So that's the time, and I need to put a negative there in order to make sure that's okay. Lambda comes up to be this value. Once I have that, then I can turn around and solve for time. So the natural log of 8, and then divided by minus lambda, which is 0.012 days to the minus 1. And then I've got the time. So I come up with 9.88 millicuries. Part B, the activity here is after 30 days. So the difference that I'm going to, this activity here, that same, let me start again. The lambda here is not going to change because it's already based on the decrease in activity, regardless of however many days we're looking at here. So if I want the activity, oh wait, we're solving for activity here, so that's my bad. I should have solved for the activity. Okay, so I know in this particular case, I know lambda. I don't need the time. Sorry, got confused. Let's take that out. Let's go here. So once I know what lambda is, then for part A, let's go back to that. I know that the initial activity, this is problem 12, the initial activity is 10 millicuries. That is E to the minus 0.012 days to the minus 1 times 1 day. Multiplying all that out, then I should come up with 9.88 millicuries. The decay constant here is not going to change for part B. The only thing that's going to change for part B is the fact that I'm working with 30 days. And then that's computing through, substituting this value in for lambda here. This is what I come up with. So that's, sorry for the minor distraction there, but that's where these that's where those answers come from. Now let's move on to number 13. We've got a sample here of cesium-137 that initially contains 1,000 atoms. So what is the value of the decay constant for this isotope? Now, for this problem, I need to go through and I need to give you what the isotope half-life is. And I don't think I did that in the problem, so I need to do that. But in order to find the value of the decay constant, again, this is if I know what the half-life is, I can use this particular formula and it comes out to be that. But I do need to, and that's a little bit different from what we got here. So that's an update I need to make in the homework assignment. How many does the sample contain after 2 years? So if I want to know what the number is, not e to the minus lambda t, then I know that I start with 1,000 atoms, e to the minus 0.022975. Times 2. Evaluate that expression, and I'll come up And basically it truncates to 955. So for part C, the change in N, basically I've gone to 955 atoms from 1,000. So the change in N is essentially going to be minus 45. Here you can see my computations, it comes up with a fraction, but you don't really have a fraction. You deal with whole numbers here, so it's minus 45. For part D, they're wanting to verify this particular relationship, which was very useful in the first problem that we were working here. Here they're saying it's an approximation. The approximation is if I know what the change in atoms is and I know what the amount of time is, I'll come up with this answer. If I take lambda and multiply it by the original number of atoms that I started out with, I'll come up with this. This is fairly close to that, except I believe I'm missing a minus sign here. Sign front. So there we go. They're saying verify the equation by substituting those values in and see if you're pretty close, which in this case you are. So now on to number 14. Guess that's as low as it goes. So we've got a radioactive source that has a half-life of 74 days and an activity of 370 megabecquerel. What was the activity 30 days ago? This is an interesting little problem. So the activity 30 days ago. A lot of times when we write these particular formulas, we think about it going forward. In other words, this is decaying. Well, what happens if we are wanting something that is back in time? What do? Well, how about we do this? We take, first of all, we go through and try to figure out what lambda is. Again, it's natural lambda 2 divided by the half-life. You run this particular formula, this is what you come up with. Here, what we're going to do is we're going to take 370 megabecquerel, and we're going to multiply that by minus 0.0094 days. Yeah, this is getting a little muddy. Times, and this is 30 days ago. So let me write that out here with a little bit more room. There we go. That should be what you come up with. What happens is this exponent has a negative times a negative, and it becomes a positive, and it's also going to be greater than 1, or well, just because it's positive, we're going to take this, it ends up multiplying this by a number that's greater than 1, and we end up with that particular value. We should end up with something that's greater than that. So that's a solid check there, make sure we're doing things okay. So now let's go to number 15. A radioactive source has a half-life of 60 days. What is the relative activity after 1 week? Now, again, what are we looking at here as far as relative activity is concerned? We're going to go back to ad nauseum to the equations here. The relative activity is basically going to be the percentage of activity then or now to what it was back then. This is going to be equal to this. So let's see, this is 15. The half-life of this radioactive source is 60 days. Again, to find lambda, we go through this particular formula. So we take the natural log of 2 divided by that, and we come up with this. So the relative activity is going to be equal to minus 0.0116 days. Okay, let's stop with the chicken scratch here. Let's try. And then how long is this going to be for? It's going to be for 7 days because it's 1 week. And if you run through the computations here, you come up with about 92%. Okay, problem 16. We've got an 11 Curie iridium 192 source, and it is received on August the 20th. Regulatory requirements do not allow use of the source until its activity is 10 Curie or less. So on what date will the source reach this particular activity? Now we're going to be looking at whole days here. We're not looking at half days or, when this starts, because we have labor laws and things like that as far as when things will begin. Now, one thing I will say here is that I, again, had to go through and look up exactly what the half-life is on this. So I need to give you that here in this particular problem so that your computations are going to match pretty much what this needs to come out to be. So let's take a look here. The half-life here is 74 days. Again, finding lambda. You can see here basically natural log of 2 divided by that value is what gives you lambda. We know the activity when we received it. We know the activity when it is to be used is this. So what we're going to do is we're going to use good old activity formula here. So we know A divided by A naught. It's going to be this. So we are going to try to figure out what time is. Again, we go through, we take the natural log, both sides. I'm going to bring the coefficient down already. That did not 0, that's 1. So solving for time, we get the natural log of A divided by A naught. It's lambda. I know what lambda is. I know what this ratio is, which is going to be 10 divided by 11. So what I should end up here with is a natural log of 10 divided by 11. The units will cancel out, minus 0.0094 days to the minus 1. When you compute that, you come up with 10.2 days. We're going to round that up, and we're going to call that 11 days. So basically what that means is we go from August 20th to August the 31st. That's when it's allowed to be used. Okay. Now, problem 17. So we got a patient that's had a 25 millicurie iodine 125 permanent seed implant 3 years ago. So what's the activity? This again is something where I disagree here with on the book, and I think it, or at least with this answer, and I think it's because of what we're using for half-lives. Half-life in this particular case is going to be 59.49 if you look it up. I'm going to standardize that value for this particular problem. We know what lambda is. Again, lambda is going to be computed, and you may be sick of hearing me say this by now. It comes from that. So this is the activity when it's implanted. We have here the number of days, which we could take that and turn this into years if we really wanted to, since we're looking at a problem here that it was implanted 3 years ago. But what we're looking at is the activity, the time is going to be equal to the original activity minus times e to the minus lambda t. We know that the original activity is 25 millicuries. E to the minus 0.0117 days minus 1 times 3 years, except I don't put in 3 years. I will put in 365, and you could put in 0.25 times 3. When you do that, you should come up with this. And let's check that to make sure that that's exactly what I did. 365.25. And the reason I put the 0.25 in there is to account for the fact that we actually, the day is a little bit longer. We have about a quarter of a day longer in each year, and that's why we have the leap year. We have 1 full day in order to be able to catch up. So this is what we have in terms of nanocuries. Now, originally, when you put that in there, you would end up with this number of millicuries. But if I'm going to write this in a unit that's a little closer to being in scientific notation, nanocuries is really what we're going to be looking for here. Seem to have, let's see, we've got 25 millicuries. We've got 0.07 okay, that seems right. Let's see if I don't think the nanocuries actually here is right. I think actually what we are looking at here, if we wanted to get something that had scientific notation, we're going to have to multiply by this in order to get something that's even close to that. And as we go from micro, if we were to take that and divide that by 1,000, we end up with nanocuries. If we take that and divide that by another 1,000, that's where we end up with the picocuries, because otherwise we end up with the wrong answer. So I again am going to disagree with that particular value. I believe this follows the logic more closely. I will do an update on that on the assignment. All right, problem 18. For a prostate seed implant, and I have no idea why they put seed in parentheses there. Iodine 125 seeds with an activity of 0.350 millicuries are needed on the day of the implant. The seeds are to be delivered 1 week prior to the implant. So what activity should the seeds have on the day of delivery? Well, again, I'm going to use the same half-life as before. Lambda is going to be the same as what it was before. This is the activity when it's implanted. So essentially, what are we going to need to receive in order to be able to do this? Well, we know our formula here. We also know that if we want to solve for this, that we take this garbage and throw it over here on this side. So we know here that, and we've got minus 0.0117 days. times 7 days. We should end up with a higher activity here than on the day of the implant. And that's to account for that 7-day lag. Okay. All right, now we've got one last problem here we need to go over. And this is the one on problem set 3. So let's jump out of this. And let's go to problem set 3. This is basically a rewriting of this, except you don't have to mess with all of this junk. So what's the wavelength and frequency of a 1 MeV photon? All right. What do we know? We know that the energy of the photon is 1 MeV. Here are a couple of other things that you're going to need. H is going to be represented with Planck's constant. Planck's constant, if you look it up and you want it in EV/seconds, this is going to be the value. Also, when it comes to the speed of light in a vacuum, this is what we're going to be using, and it's going to be meters per second. This is going to be represented using the letter C. Now, we know that the energy of a photon is h nu. If I know this, and this is a constant, I should be able to figure that out. And how do I figure that out? Well, I take E and divide it by H. So when I take E and divide it by H, I am taking 1 MeV and dividing it by 4 point, and bear with me here, 4.136 times 10 to the minus 15th. Obviously, this being an MeV, I need to change 1 MeV into EV, and I'm going to put that over 1 MeV is equal to 1 times 10 to the 6th EV. So this is the saying is 10 to the 6th EV. So my frequency is going to be 10 to the 6th EV, all divided by 4.136 times 10 to the minus 15th EV seconds. So why did I need that? I need those units to cancel. And it turns out you end up with 2.42 times 10 to the 20th seconds to the minus 1. Or another way of saying that is going to be 2.42 times 10 to the 20th hertz. Okay, so that's the velocity. And that's the same thing, and you can see it over here right there with that. Now, we figured out the frequency. What about the wavelength? How do we get at the wavelengths? Well, we're going to use another relationship here, and I'm not sure exactly how familiar you are with it or not, but here we go. If you take the frequency times the wavelength of a photon, you should get the speed of light. This means that in order to get that, we know what this is now. We can now solve for this by saying speed of light divided by nu. We can do that, and you should come up with that particular relationship. Another way to look at it is if I know this is true, and I know that this is true, if I solve this, then I find out that I can take H times C divided by lambda, which means that lambda is equal to HC over the energy. And if you multiply this by this, and then divide by this, which obviously needs to be changed. So I've got 1.436 times 10 to the minus 15th EV seconds times the speed of light squared, which is going to be 2.998 times 10 to the, and I'm running out of room here, to the 8th meters per second. All that divided by 10 to the 6th EV. You should come up with this particular result, and it will be in meters because the EVs will cancel, the seconds will cancel, and you're just left with the meters here. Okay. Hopefully that helped a little bit. I'm sorry for my chicken scratch type of writing, but that's that is in fact the solutions that I have come to for these particular problems. And I hope this helped.